Radiation occurs when an excited electron, in a surface molecule, or atom, drops to a lower orbital, generating a magnetic field, which, in turn, generates an electric field, and so on. Hence an electromagnetic wave results, and this is propagated through vacuum, or a gas, until it encounters an absorbing surface. At this surface, an electron can be excited into a higher orbital, increasing the energy, and hence the temperature, of the absorbing surface. The excited electron, in the right-hand side surface, can now drop down back into the lower orbital, and the same energy can be radiated, back to the other surface from where it came. Surfaces can therefore emit, and absorb, radiation, at the same time. The wavelength of the radiation decreases with increasing temperature of the radiating surface. In this diagram, you can see that, as the temperature of the surface increases, from 50 Kelvin towards 5800 Kelvin, the wavelength of the radiation, corresponding to maximum power, decreases from about 60 micrometers, to about 0.5 micrometers. (5800 Kelvin) is the temperature of the Sun's surface, which results in radiation, or light, being emitted, and this radiation is visible to you between 0.38 and 0.78 micrometers. In fact, your, and your forefathers', eyes have evolved to see these radiation wavelengths. For a given surface temperature, radiation is emitted over a large range of wavelengths. The energy flow rate of the radiation, E(b), in watts per unit area, is represented by the area under the curve for a given surface temperature, denoted by T. This specific rate can be obtained by integrating the curve from a wavelength of 0 to infinity. Multiplying by the radiating surface area gives you Q radiation. This is known as the Stefan-Boltzmann's law. B indicates that this is for an ideal surface, that often appears perfectly black if you look at it. For non-ideal surfaces, the formula must be multiplied by the emissivity. Radiation from the surroundings will arrive at a surface as G, the amount of watts per square meter. In order to obtain the radiation absorbing rate for an ideal black surface, which would absorb all the irradiation, you have to multiply G with the area, A, of the surface. For other, non-black, surfaces, you have to multiply the irradiation by the absorptivity, alpha, to get the rate of radiation energy absorbed. Radiation can be reflected, transmitted, or absorbed by the irradiated surface. You should be more interested in the fraction of radiation that will be absorbed, because heat transfer has then taken place, and this will be determined by the absorptivity, alpha, as shown. Consider a large non-ideal enclosure at a constant temperature T2, i.e. steady state conditions. Heat emitted by the surface will be equal to heat absorbed by the surface. Further, assume that the surface is gray, so that the emissivity and absorptivity are equal. This is probably reasonable, as the radiation is generated at the same temperature as the radiation is absorbed. See the literature on non-gray surfaces. The absorptivity and emissivity are different due to temperature differences of the surfaces involved. This means that the radiation in the open space, G, is equal to sigma times T2 to the power 4. Now you put a small body, at temperature T1, inside these large surroundings, small enough not to affect G equals to sigma times T2 to the power 4. The small body will radiate heat from itself to the surroundings, resulting in Q, 1, 2, 2. For a large surroundings, you only have G irradiating the surface of the small body, and a little bit of extra heat that originated from the small body but was reflected back from the surroundings. You can ignore this reflected heat, as it will be small if the surroundings are very large. Alpha times G times the area of the small body will be absorbed into the small body as Q, 2, 2, 1. The net rate of radiation heat loss is the difference between the heat emitted by the small body and the heat absorbed. If the small body is also gray, then a further simplification of the formula is possible as shown. The table provides net radiation heat rate equations for gray surfaces. In this example, the heat conducted through the solid is removed via the combined effort of convection and radiation. Bear in mind that you have to use the moving fluid temperature for convection and the surrounding surface temperature for net radiation in the equation.